And here we go. So the name of the chapter is called The Statistical Models in Simulation. And the outline is as follows. First, we are going to give a fast definition of the random variable concept. Then we are going to cover the discrete and the continuous random variables that we have known from our earlier classes. This is just going to be a revision chapter. However, there are some important aspects that I especially would like to emphasize, and we are going to use some of the concepts that we are going to revise here in the following weeks of this course. So at first, let's talk about the definition of a random variable. Actually, first we need to define the concept of randomness. So consider an experiment, and that experiment is going to be a random experiment, which means we cannot predict the outcome of that experiment exactly before performing it, and there is an inherent variation in the outcomes of this experiment. So we actually have a list of possible outcomes for that experiment, and we cannot exactly know which of these outcomes will be observed if we perform this experiment. Now, the sample space of that experiment is the list of the outcomes. If we can create a set from the possible outcomes of that random experiment, that is going to be called the sample space. And usually for random experiments, the sample spaces consist of qualitative outcomes. Okay, for example, if you think about the weather condition, tomorrow can be sunny, rainy, foggy, or cloudy or snowy. Okay, there are many possible outcomes, of course, with different probabilities, but there are many possible outcomes which are given in a qualitative expression. And usually we are interested in quantitative functions of the outcome. So we are talking about the quantitative representations of the outcomes instead of the actual outcome itself. For example, when you toss a single regular die, actually the outcome of this experiment is just one of the faces to be upturned, right? But when you write down integers in each side of the die, then it is just going to be a quantitative function of the outcome. So to the faces of a die, instead of writing numbers, if you just color the faces with different colors, then the outcome itself is just going to be the name of the color. So we are quantifying the outcome by writing a number on the faces of a die. And this is called a random variable. A random variable is a real valued function defined on the sample space. If the outcomes are converted into real values by defining a function, that function is called a random variable. Consider the experiment where we are tossing two dice at the same time, and we know that the sample space of this experiment would have 36 equally likely outcomes, assuming that the dice are fair. Okay, so we have this sample space consisting of 36 outcomes starting from 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, so on and so forth until 6, 6. So we have 36 outcomes, each of which has the same probability, which is 1 over 36. Now we are defining a random variable, which is the sum of two dice. Now the outcomes in the sample space are represented in the form of two values given as a couple. So actually these outcomes are not quantitative outcomes. Now I will define a random variable over the sample space of this random experiment, which is the sum of two dice. For example, when you get a 4, 5, the sum of two dice will be 9. And that is just going to be a quantitative function of the outcome itself. Another random variable can be the absolute difference between two dice. For example, when you get a 6, 2, the absolute difference between the two dice is going to be 4. Even if you get a 2, 6, still the absolute difference between two dice will be 4. Another random variable can be the maximum of the observed values. If you get a 3, 5, then the maximum will be 5. And another random variable, W, can be the minimum of two dice. You can define many different functions over the outcomes on the sample space to define different random variables. We know that the value of random variable is determined by the outcome of the experiment. For example, if we are talking about random variable x in the previous page, which is the sum of two dice, the event of x being equal to 2 can only happen if you get a 1-1. Or the event of x to be equal to 9 can only happen if you observe one of these four outcomes. Or if you want x to be equal to 11, then you need to observe one of these two outcomes, either a 5-6 or 6-5. So because the value of a random variable is determined by the outcome itself, we can assign probabilities for the random variables to have an equation or inequality statement, right? So the probability of x being equal to 5 is the probability of getting either one of these four outcomes. So either one of these four outcomes has the chance of 4/36 because there are 36 equally like the outcomes in this random experiment, and four of them corresponds to the random variable x to be equal to 5. So on and so forth, we can define the probabilities on random variables by calculating the probabilities of the underlying event. So for x to be equal to 4 is represented by an underlying event defined on the underlying sample space. Okay. So basically, probability on random variables is a function. So let's explain that function. We have a sample space. This sample space is the set of all possible outcomes of the random experiment. And x, the random variable, is a function which converts the outcomes into real numbers as a quantitative value. So we have 1, 3 here, 1, 3. That outcome is converted to the value of 4 by random variable x. So x itself is a function. And 2, 2 is converted to 4 as well by that random variable. So basically I am asking this. What is the x of 2, 2? The x of 2, 2 is 4. What is the x of 6, 4? The x of 6, 4 is 10. Therefore, that x is a function which converts the outcome to a value based on the definition of the random variable. After converting the outcomes into real numbers, then the probability function relates these real values to a value within the unit interval, and that function is called the probability function. So it relates the real numbers which are to be assigned for the random variable to the unit interval to define probabilities on it. So I'm not going to explain the details and the axioms and of the probability. There are some basic assumptions about the probability function that we need to believe in altogether, so we may meet in a common ground on probability. However, this is not a part of this course. I'm just providing this chapter for a fast revision. And the question here is asking that we are going to have two fair coins, which means each coin has a 50-50 chance to get a head or tail. And we are defining a random variable y as the number of heads appearing. Now, when you toss two fair coins, either you get 0 heads or 1 head or 2 heads, right? So the number of heads that you may observe can change between 0, 1, and 2. So the question here is asking this basically, what values can y take with what probabilities? So what we know is y can take values of 0, 1, and 2. So here's the question, when y takes the value of 0? If we observe double tails, then y will take the value of 0. When y takes the value of 1, if we observe a tail head or head tail in the ordered sequence, then y is going to take the value of 1. And when y takes the value of 2, if you observe a head. Actually, we first need to define the sample space of this random experiment. This random experiment is the tossing of two fair coins, and by the basic principle of counting, each of these coin flips will have two outcomes, and by 2 times 2, we are going to have 4 possible outcomes for this random experiment. These are going to be double tails, double heads, first getting a tail, then head, or first getting a head, then tail. Now we know that in this sample space, each of these outcomes are equally likely to occur because we have fair coins. Now a random variable here converts each of these outcomes to a real value. So because the random variable y is defined as the number of heads appearing, how many number of heads do we see in a tail-tail outcome? 0. How many heads we observe in a tail-head or a head-tail outcome? 1. And how many heads do we observe here? 2. So the random variable converts these outcomes to real numbers, and the probability function assigns probabilities to each of these outcomes. What is the probability of y being equal to 0? That is equal to the probability of the underlying event. The underlying event is containing only a single outcome, which has the probability of 0.25. Now, the probability of y being equal to 1 is determined by the underlying event. The underlying event contains two outcomes in the sample space. This event would have 0.5 probability. And finally, the probability of y being equal to 2 is equal to the probability of the underlying event of getting a double head, which has the probability of 0.25. So both the random variable and the probability is a function. Sample space, the real numbers, and the unit interval are the sets, and random variable converts the outcomes into real numbers, and the probability function converts these real numbers to the unit interval values, the values in unit interval, which are called the probabilities. Now, we need to talk about a distinction between the random variables. So there is a general classification of them. There are discrete random variables and continuous random variables. Because the definition of these random variables are different and the conceptualization of them are also different, we are going to study these random variables in two different phases of this chapter. Okay, so how do we get the distinction between discrete random variables and continuous random variables? In the previous example, we defined the random variable over a sample space, right? Now you see in this sample space, we have 4 elements. The number of elements is countable, but there are some sample spaces which are uncountable, which means we cannot count the number of possible values of the random experiment. We can only measure the possible values, okay, but we cannot ask how many. So there will be some random experiments like that as well. At this point, we need to define which sets are countable and which sets are uncountable. Now, what is the counting process basically? A set is countable if its elements can be put in a one-to-one correspondence with the sequence of positive integers. So you see, I can say that this set is countable because I can label this outcome with 1, I can label this outcome with 2, I can label this outcome with 3, and I can label this outcome with 4, and I can say this set is countable. Now, there are some sets which are uncountable. Now, I would like you to answer this question. So imagine these real numbers between 0 and 1. So this is a set, right? Real numbers between 0 and 1 is a set. Can you count how many real numbers between 0 and 1? Actually, it is impossible because they are uncountably many. It is not just infinite. The number of elements here is not just infinite. It is uncountably infinite. There are also sets which have infinite elements but still countable. For example, the positive integers itself, even though a set has infinitely many elements, still it may be countable. What is a discrete random variable? A discrete random variable is a random variable which can take on either a finite or a countable number of possible values. Now you see, let's imagine this random variable x. The number of heads that we observe in 3 consecutive coin tosses. What are the possible values of x here? So in the 3 consecutive coin tosses, the number of heads can be either 0 if you get a 3 tail, or 1, or 2, or 3 if you get 3 heads, right? So there are 4 possible values that it can take. So the random variable here, x, can take on a finite number of possible values. Now, let's look at the second example. Why? The number of clients entering a bank between 8 a.m. and 5 p.m. So the time between 8 a.m. and 5 p.m. is basically the workday in that bank, the time that the bank is open to clients. Now, Y can take how many different values? First of all, on that day, nobody can enter. It is possible, right? So nobody would be interested in doing anything in that bank on that day. Now, it has a very low probability, but still it is possible, right? So on that day, there may be only one client arriving, or two clients maybe, or three clients, four clients, five clients. Can you put an upper bound? Can you put a theoretical upper bound to that? I mean, can you just say no more than 100 clients can enter, or no more than 10,000 clients can enter to that bank? Actually, for you, it is impossible to say that thing because we do not know how many potential clients are there to enter the bank, and we do not know if some of them are not going to enter the bank later again on that day, right? So it is possible to have infinitely many clients in that bank on that day to enter. So here's the thing. How many different values Y can take? So it can take non-negative integer values, right? And there is not an upper bound here. This random variable is taking infinitely many values, but a countable number of many values, right? A countable number of possible values, because I can basically count these elements. This is my first element, this is my second element, third, fourth, fifth, sixth. So it goes to infinite, but still countable. So countable means what? If elements in a set can be put in a one-to-one correspondence with the positive integers, or if you can label each element with a different positive integer, then you can say that that set is countable. Now, if a random variable can take on a countable number of possible values or a finite number of possible values, then that random variable is called to be a discrete random variable. For continuous random variables, we say that if a random variable can take on a continuum of possible values, or continuum means an uncountable number of possible values, that random variable would be a continuous random variable. For example, if we define the random variable x as the lifetime of a battery in hours, so working lifetime until it completely exhausts, so x can take theoretically any non-negative real value. So it can work for 0 hours, maybe it has already been exhausted, or theoretically we cannot put any upper bound for the lifetime of it, so we do not know how much energy does it have, or we do not know in which type of device we are going to test it. Maybe it is just going to work for a very, very long time, so there is not a theoretical upper bound of it. Even if you can put a theoretical upper bound, still in an interval over the real line, there are uncountably many possible values. So we are talking about a duration, so the length of time. The length of time itself naturally is a continuum, right? So there are uncountably many values that the lifetime can take. In fact, if I ask you to count the time, you should answer me, I cannot count the time. I can only measure the time, right? If the value of a random variable is not countable but measurable, then that random variable is a continuous random variable. So the daily profit in dollars. Now, of course, you can ask me, we can count the money. Yes, you can count the money in dollars. However, the daily profit can have a very, very large resolution. I mean, if you are going to gain an interest from a money on that day, you can gain a interest given in a continuous values, right? So therefore, and it is just taking real values only. Even if you say, I can also model the daily profit in dollars as a discrete random variable if I just focus on the quantities in dollars and cents, yes, you can do that, but it is just going to be a very, very complicated function. Still, we are assuming that the amount of money is measurable. So the length, the weights, okay, the time durations, they are all continuous values which are measurable. Therefore, if they are random, they are usually modeled by continuous random variables.